Alright, problem set 19 here, where we're going to discuss isomers. So, let's talk about what isomers are. Here we asked us to define isomers. Isomers are just two molecules that have the same chemical formula, but they're different molecules. Now, there's multiple ways to meet those two criteria, to have the exact same atoms, same chemical formula, and different molecules. And as a result, there are different types of isomers. So I'm going to jump over here and let's break down a little category tree for isomers. So our first split is going to be, here we're going to have constitutional, which is also called structural. And over here we're going to have stereoisomers. Stereoisomers is going to split into enantiomers and diastereomers. And then diastereomers is going to split further into conformers or conformation isomers and geometric. Now I'll talk about what all those are. First thing I'll say though is for Chem 105 we don't really care about conformation isomers. Alright, so constitutional and structural isomers. What that means is that your atoms are structured or are connected differently. So basically if I have this molecule and that molecule, okay, those have all of the same atoms. They're both C4H10 if you were to count up all of the carbons and implicit hydrogens. Okay, but these atoms are connected to each other differently. Okay, hopefully that's pretty easy to see. To figure out if things are constitutional structural, you'll just take your two molecules, figure out their chemical formula based on the atoms in them, and just making sure that they're not the same atom or the same molecule. As long as they're different and they have the same formula, you know that they will be, as long as they're connected differently, you know that they're constitutional or structural. Okay, that brings us to geometric isomers. Geometric isomers have to do with a double bond. So if I were to give you these two molecules and ask if they were isomers, the answer would be no, because they have the same chemical formula, C4H10. Okay, but they're not different molecules. They're exactly the same, okay, because single bonds can twist. And so you can imagine if I twisted that single bond, it would bring that guy up. And as a result, these are exactly the same. But double bonds cannot twist. Okay, so if I were to give you these two molecules, okay, these are now have the same chemical formula. These are C4H8. Okay, and they're different molecules because one, the double bond locks it up and the other locks it down. We call these cis if the two branches are going on the sticking out the same side. So if I drew a line down my double bond, my two branches are going on the same side of that line. That's cis. If they're going on opposite sides, those are trans. And those are geometric isomers. So requisite for a geometric isomer is a double bond. Okay, and that brings us to enantiomers. An enantiomer requires a chiral carbon. A chiral carbon is a carbon atom that's connected to 4 different things. Okay, and we'll get some practice later on in the problem set, I think, identifying chiral carbons. But if you have a molecule with a chiral carbon and you take the mirror image of that molecule, you have a different molecule. So let me give an example of something that is not an enantiomer. So this carbon is connected to, has 3 connections to, actually let me make, let's make this a fluorine. To 3 different things. If I were to take the mirror image of it, Okay, this guy and this guy are the exact same molecule. You can imagine if I just took this on the right side and flipped it over, okay, I would get this guy. Okay, so most molecules, if you take the mirror image of them, they are the exact same molecule. However, if you have a chiral carbon and take the mirror image, you get a different molecule. So let's see how I'm going to draw this. So I'm going to draw this carbon. It's going to have an X here. I'll say W X, and then okay, what this wedge and dash means, the wedge means that Y is actually coming out of the board, and Z means it's going into the board. Okay, so this Y and Z should really be drawn right on top of each other. Okay, but in order to show the kind of three-dimensional shape, Y is coming out, Z is going in. So this is chiral because it's got 4 different groups. If I were to take the mirror image of it, okay, these are now non-superimposable. So if you can imagine, if I just took this molecule on the right and slid it over to the left, the Y would match with the Y here, and the Z would match with the Z here going into the board. But this X would be with that Y, and this X would be with that W, and this W would be with that X. So that would not be the same molecule. So then instead of just sliding it over, what if I flipped it over so that this W flips over to that W and this X to that X? Well, now I flipped the top. Ooh. So if I were to, sorry about that, if I were to flip this over so that this W flipped to that W and this X then was on that X, well, this Y would get flipped around and be with the Z. Okay, so moral of the story is that if you have a chiral carbon and you take the mirror image of that molecule, you get a different molecule. Therefore, these have the same chemical formula and they're different molecules, and so they're isomers, and specifically they're enantiomers. So again, on this left we have constitutional and structural isomers, which means that they have the same formula and they are connected differently. Stereoisomers, however, are connected the same. Under that we have enantiomers, which are mirror images of each other. Okay, diastereomers are not mirror images, okay, because diastereomers have cis-trans. Okay, so if you think about it, these are connected differently. These are all connected the same, meaning this carbon's connected to the same 4 things in both molecules. So they're different for different reasons. One is chiral carbon, the other is a double bond. All right, so let's dive in back into here. What is the difference between a constitutional isomer and a stereoisomer? Constitutional isomers are connected different. And stereoisomers are connected the same. What's the difference between a diastereomer and an enantiomer? So that's over here, diastereomers versus enantiomers. Enantiomers, I guess you could say enantiomers are mirror images. Diastereomers are not mirror images. Now there's like different ways you could answer this question, but that makes sense to me. All right, draw all 4 constitutional isomers of butane. Butane is actually, okay, this should say butene, which doesn't really matter because you probably haven't learned how to name them anyway, but C4H8 is butene, not butane. All right, so C4H8, if I were to draw 1, 2, 3, 4 carbons, how many hydrogens would there be? So that's C4, and there's 3 hydrogens, 2, 2, and 3, so that's H10. Okay, we want H8, so what's one way to get rid of 2 hydrogens? Draw a double bond. Right, because now this carbon lost 1 hydrogen and this carbon lost 1 hydrogen, so this is now C4H8. So that's butene, C4H8, and we want to draw 4 constitutional isomers, so 4 other ways of drawing C4H8 that are not the same as that. So I could put the double bond there. That would be different. Could I put the double bond there? And the answer is no, because this is exactly the same as that. Those are the exact same molecule, just flipped. So as a result, that doesn't count. Okay, other ways that I could do this, I could do this and stick a double bond on one of those. And the last way would be could do, let's see. Oh, I could do a ring. So just like a double bond gets rid of 2 hydrogens, a ring gets rid of 2 hydrogens. You imagine if I had this carbon would have 3 and that would have 3, and then when I close the ring, this carbon would have 3 and that carbon would have 3, and then when I close the ring, each of them lose 1 hydrogen. So that would be 4 constitutional isomers of butene. Oh, and it says including the cis-trans isomers, so I guess you could also draw that guy. This would be the trans version, that's the cis version. Draw 5 constitutional isomers of C6H14. So C6H14, 1, 2, 3, 4, 5, 6. How many hydrogens? 3, 5, 7, 9, 11, 14. So that's C6H14. Okay. Now, how could I make a constitutional isomer? Well, this is all I can do with a long 6 carbon chain. So let's go to 5. 1, 2, 3, 4, 5. And now I have an extra carbon to deal with, so I could put it there. I could put it there. Could I put it there? Nope, because those two are the exact same thing. Whoa. Could I put it there? Nope, because those two are the exact same thing. Because remember, single bonds can twist. So that's everything I can do with a 5 carbon chain. So let's go to a 4 carbon chain. 1, 2, 3, 4. Now I have 2 carbons to deal with. I could do 1, 2. Okay, and that gives me my 4th structure. They want 5. So I could, 1, 2, 3, 4. So you put them both on the same carbon. There are 5 nice constitutional isomers of hexane. And remember, structural and constitutional mean the same thing. So 5 structural isomers of C7H16. So 1, 2, 3, 4, 5, 6, 7. You count up the hydrogens, you get 16. So there's one of them. So I go 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, and stick it my 7th there, or 1, 2, 3, 4, 5, 6, put my 7th there, 1, 2, 3, 4, 5, 6, put my 7th there. Nope, these two are the same. Can't do that. So that's everything I can do with 6. So 1, 2, 3, 4, 5. I could do 1, 2. 1, 2, 3, 4, 5. I could do 1, 2. So that's 5, but I could also do 1, 2, 3, 4, 5 and do 1, 2. Or 1, 2, 3, 4, 5 and do 1, 2. So lots of options. Just make sure that you're not drawing the same molecule twice. Alright, state the relationship between the molecules. Are they constitutional stereoisomers, same molecule or different molecule? Okay. The best way to do this first is we got to figure out, are these different molecules or are they isomers? Isomers have to have the same chemical formula. So let's figure this out. So here I've got carbon, 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 carbon. So this guy is C6. How many hydrogens? Well, I've got 3 there, 2, 1 there, 2, 2, and 3. Remember, every carbon needs to make 4 bonds. So any bonds that aren't shown have to be hydrogens. And then I've got 1 there. So this is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, I can do the same thing here. Carbon, 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 carbon. C6. 1, 1, 2, 3, 2, 2, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, awesome. So these have the same chemical formula. So we know that they are not different molecules. Or we know that they are, yep, so they are different molecules, but we know that they are isomers. Okay, so then are they the same molecule is the next question. How could they be different? Well, they could be different by being connected differently. They could be different by having a double bond. The way we draw these images without any wedges or dashes, it would be impossible to tell if they're mirror images of each other, and so that's really not an option for this question. So really we're saying, are they cis-trans? Or are they constitutional isomers? Or are they just different molecules of the same molecule? Here we have this OH coming out, and it's coming out of the 1, 2, 3rd carbon. Here we have an OH coming out of the 3rd carbon as well. And so the result of that is that these are actually the same molecule. Okay. Let's figure out here. Here we have 1, 2, 3, 4, 5, 6. H is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh. Here we have 1, 2, 3, 4, 5, 6 carbons. Hydrogens, we have 2, 4, 6, 8, 10, 11, 12. Alright, so we can stop right there. We have different numbers of hydrogens, and as a result, these are just different molecules. They're not isomers of each other, because isomers would need to have the same chemical formula, and these don't. Here, this is C6, H2, 4, 6, 8, 10, 11, 12. Oh, and this is C5, 6, H3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alright, so these are not different molecules. So they could potentially be isomers. And actually, you see these are obviously connected differently. And therefore, this has got a ring of 5, this has got a ring of 6. So these are going to be structural, constitutional isomers. Okay, alkanes to the right are cis-trans. Label which is cis and which is trans. So really what we're doing is we split the molecule. We look at the right side and say which of the two branches is bigger. That one's bigger. The left side, which is bigger. That one's bigger. Then we draw a line this way and say, are those two big things on the same side or opposite sides? Those are on opposite sides, so this must be trans. Do the same thing here. On the left, where's my bigger thing? That. The right is that. Those are on the same side, so this is cis. Which of the following objects could be chiral? Okay, so remember, chiral means that if you take a mirror image, it's different. Okay, so if I take the mirror image of a golf club, well, that depends on what golf club you're talking about. Let's talk about like a big driver, fancy golf club. If I take the mirror image of it, you're going to get a different thing. You can't turn that mirror image in any way that it could fit right on top of the original. So golf club could be chiral. Spoon, if you take the mirror image of a spoon, you could just slide it right over and it would fit inside itself. It's superimposable, so that would not be chiral. A glove would be chiral because our hands are mirror images of each other, but there's no way that you could line your hands up where one could, in theory, fit right inside the other. Shoes are going to be chiral, okay, because there's a right-footed and left-footed. A deadbolt key, okay, if you were to take the mirror image of a key, for example, if I have a key with all the ridges, and I take the mirror image of it, these ridges are often not symmetrical. If I was looking straight down from the top at the key, often you have the left side looks different than the right side does. I don't know what that picture was trying to show, but basically a key is going to be chiral. A screw is also going to be chiral because if you take the mirror image, you get the corkscrew going up a different direction. Baseball is not chiral. Spiral, seashell would be chiral. There you go. Okay, now which of the following molecules are chiral? Circle the chiral center. So really, if we're trying to find out if a molecule is chiral, we're just looking for chiral centers. Is there any carbons connected to 4 different groups on the molecule? So we have this carbon. We've got group 1, group 2, group 3, group 4. Those are 4 different groups, so the mirror image is going to be different, so those are chiral. Here, okay, so this is kind of tricky to see, but if I were to break this down, that carbon's connected to 3 things, so that can't be chiral. That's connected to 3 things, so not chiral. Also 3, also 3, also 3, also 3. This carbon's connected to 4 things, but 3 of them are the same, so that can't be chiral because I made 4 different things. This carbon right here, it's kind of hard to see, but you've got one branch that way, that way, that way, and then to this white guy. And so, in each of those branches are different, and as a result, that's a chiral carbon. And likely are the same right there. So this one is chiral. So, and I should circle that's chiral and that's chiral. Okay, here we've got a carbon. It's connected to 4 things, but hydrogen and hydrogen are the same. And as a result, these are not chiral. Okay, here's a carbon, but it's only connected to 3 things. So that's not chiral. Here's a carbon. This one here is connected to 4 things, but these 3 are the same, so that's not chiral. Here's a carbon, we got connected to 4 things. I don't know if you can see that, but we have this group over here, this group, this carbon with 3 hydrogens, and this hydrogen. So that is going to be chiral. Okay, here we go. This might be a little bit easier to see. So let's figure out which of these are chiral carbons. So remember, I need 4 different groups. And groups refers to the entire chain connected to the carbon. So just let me give you a small example here. If I had this, if I'm talking about that carbon right there, if I'm wondering if that carbon is chiral right now, actually let me do that. I'm wondering if this carbon is chiral. So remember, it's got this group, it's got that group, and it also has a hydrogen. Well, this group has 1 carbon long, this group is 2 carbons long, this group is 3 carbons long, this hydrogen is a hydrogen, so those 4 groups are different, so that carbon would be chiral. But what if I did this? Now I've got this 1 carbon group, a hydrogen, then I have a ring going this way, and I have a ring going this way. But if you think about, I like to imagine if I took my little dude from like Google Maps Street View and dropped him right there, and he walked along the bond. If he walked this way around the ring, he would see the exact same thing as if he walked this way. As a result, these 2 groups are identical. And if the groups are the same, this is not chiral. But what if I did this? Now, if I dropped my little street view guy and he was walking, if he walked this way, he would see 1 carbon and then an intersection. Here he would see 1 carbon, 2 carbons, 3 carbons, and then an intersection. So now this carbon is chiral. Okay, so you have to look at the whole group. Okay, so let's jump up here and do that. So first, that carbon, is that chiral? The answer is no, because it's only connected to 3 things. It doesn't have an extra hydrogen on it because it's already got 4 bonds because that double bond. So any carbon with a double bond is not going to be chiral. This guy, he's got these 2 groups that are different from each other, but he also has 2 hydrogens. So as soon as I realize he has 2 hydrogens, they're not different groups, and so that's not chiral. This carbon has an NH2. It has this junk right there, and this junk, which is different, and it also has a hydrogen. Those are 4 different groups, and as a result, that's chiral. This one has a double bond, so it's not. This one has a double bond, so it's not. All of these have double bonds, so they're not. This one, 1, 2, 3, and a hydrogen. So none of these 3 groups are the same, right? So they have this. I have this. Let's see. I have this entire thing. This entire thing. That thing and a hydrogen. Okay, the things within those blue circles are all different, and as a result, this is a chiral carbon. This carbon's got 2 hydrogens, and therefore it's not chiral. So we have 2 chiral carbons there, so that is a chiral molecule. Oh, we also have this carbon right here, but it's connected to 3 hydrogens. So. All right, over here, remember we can cross off everything that has double bonds. That leaves us with, nothing, so this is not chiral. So these dashes and these wedges, just treat them as lines. So I could just go like this, just call that a line and a line. All right, so I have no double bonds, so I can't eliminate anything like that. But I can eliminate this guy. Let me make it red, because it's got 2 hydrogens on it. So that one's out, and that one likewise is out, and that one is out. All right, so let's look at these. Remember my implicit hydrogens on there. So I've got an OH, I've got a hydrogen, and then I have the ring going that way and the ring going that way. Well, if my street view man walks this way, he's going to see an intersection to a chlorine on the first carbon. Here, he's going to see an intersection to an OH. Those are different. Some people ask, like, well, how far do I have to go? The whole thing. You just keep going until you get to the very end, really. So those two groups are different. So this is chiral. Here we have chlorine, a hydrogen. We have walking that way around the ring and walking that way around the ring. If I walk this way, I see an intersection to a carbon to an OH. This way I see an intersection to an OH. Those are different, so that's going to be chiral. This carbon, it's got a carbon to an OH, it's got a hydrogen, it's got an oxygen, and then it's got a carbon to a chlorine. Those are all different. This carbon here has an OH, it's got a hydrogen on it, it's got a ring that has an intersection to an O, and this is an intersection to an OH. Those are different. That's chiral. This carbon has all this junk is off that branch, a hydrogen, a ring this way that sees carbon, carbon, whatever, and a ring this way that sees oxygen. So those are different. That's chiral. Okay, this carbon sees all of that junk. It sees this branch to the chlorine, and then it sees a ring that way and a ring that way. And those two rings look different to a little street view man. As a result, that's chiral. Here we have OH and H. We have a ring going this way and that way. This way you see a branch to an OH. This way you see a branch with a lot of stuff off of it, and those are different. So this is going to be chiral. Here we have an OH, a hydrogen, a branch, or going the ring this way, you get a branch to a chlorine. Here you get a branch to an OH. Those are different. And this one is chiral because we get a go out to this chlorine. We've got our hydrogen. Here we have a branch to an OH. Here we just have an oxygen. So lots of chiral molecules there, or chiral carbons there. So this is a chiral molecule. Sometimes, maybe I'll just talk about this real quick, because sometimes people, they see this and they're like, okay, so they're pretty much all chiral. So when would you have a non-chiral carbon in a ring? And if you wanted a non-chiral carbon in a ring, you would have to have a very symmetrical ring. So let's say I was talking about that carbon. If I wanted that carbon to be chiral, to not be chiral, let's say I had my hydrogen and my OH, and I wanted to go around the ring both ways and have it be the same, I would need a chlorine there, and then on this one, I would need a chlorine. And then here, if I had an oxygen, then there I would need an oxygen. Okay, so these, you can tell that carbon going that way would see the exact same thing as going that way. Okay, so a lot of the times, unless you have a very symmetrical molecule on these rings, you're going to have chiral carbons, but you should always check and make sure. Okay, so that's it here. I think that's it. Yep, for isomers. Problem set 19.